Hello there, Mr. Sutton here, bringing you the AB Calculus 612 Extra Practice Number 4 solutions on areas between curves. For this problem, we want to find the area of this enclosed region. So we have f of x equals x, which is just a line going through the origin with a slope of 1. We have g of x equals negative x, which is pretty much the same thing except with a slope of negative 1. And then we have the vertical line 1. So we could graph all of these without a calculator. Calculator was allowed on this, but I'm pretty sure we can handle this one. So we're just trying to find this triangular area in here. Now again, we could use a calculator. The general idea here is we need to take the integral from 0 to 1 of, in this case, f of x minus g of x dx. But we don't really need a calculator to pull this off, right? I mean, we have a triangle here. It has a base of 2. It's got a height of 1, so 1/2 times 2 times 1 just gives us an area of 1. You could use a calculator, but it works out this way too. For this problem, we're trying to find the area of R, which is the region bounded by the graphs of y equals 2x and y equals 4x minus x squared. Let's start by figuring out where these intersect, because those are going to be our limits of integration for the integral we're going to try to set up to do this. So we have 2x equals 4x minus x squared. And I can very quickly just subtract 2x to get one side being 0. So that's 2x minus x squared equals 0. Now let's just factor an x out of that. That's going to be x parentheses 2 minus x, which gives us the intersection points 0 and 2. Okay, so we need the integral then from 0 to 2 of, let's just use this simplified everything on one side version here, 2x minus x squared. And I'm going to do absolute value of all this just so I'm ensuring that I'm getting a positive area, because I don't really know if I subtract things this way if I'm going to get a positive area. So we have 2x minus x squared dx. And let me take my antiderivative here. I can't use a calculator, so I'm going to have to do this by hand. So this is going to be x squared minus, this is going to be 1/3 x cubed, evaluated from 0 to 2. So I have all of this with 2 plugged in, minus all of this with 0 plugged in. Notice the absolute value is still there, waiting to be applied at the very end of all this. So everything in this right bracket is getting zeroed out. In the left bracket, we have 4 minus 8/3. And let's see, this is really going to be 12/3 minus 8/3, which comes out to positive 4/3. So there's our answer, which is going to be choice B. On this problem, we have these regions here bounded by y equals 2x and y equals 3x squared minus x cubed. And we're intersecting at 0, 1, and 2. We want to know which expression gives us the sum of the areas of these regions. So the basic idea is you need to do the integral from left to right of top minus bottom. On the integral from 0 to 1, the function 2x, it has a greater value than 3x squared minus x cubed. But this changes on the interval from 1 to 2. At that point, 3x squared minus x cubed, the polynomial, or at least the cubic polynomial, has a higher value than 2x. So because your top function is changing, we cannot do this with just one integral, at least if we are trying to avoid using an absolute value expression. If we're using absolute value, you could do all of this with one interval. But since it doesn't look like any of the answer choices are doing that, we're going to have to split this up into 2 integrals. For my first integral, from 0 to 1, to do top minus bottom, I need to do 2x minus parentheses 3x squared minus x cubed dx. On the second interval, from 1 to 2, which I'm going to be adding to that first integral, top minus bottom means 3x squared minus x cubed minus 2x dx. So that ends up giving us answer choice B. For this problem, we have regions bounded by the graphs of a line. It's a weird line, negative 2 over pi x plus 1. But that is a line. It just has a weird slope of negative 2 over pi. And then we also have this trig function, y equals cosine of x. Cosine is the curvy one in the graph, in case you were wondering. So we basically want an expression to give us the sum of these shaded areas. So in general, when you're finding the area between two curves, you're taking the integral from left to right, or at least that's the way we're doing it right now. And we're doing top function minus bottom function in the integrand. That's a little trickier on this problem because the top and bottom functions flip-flop about halfway through here. So if you want to actually pull this off without using an absolute value to force everything inside to be positive, if you want to get positive areas each time, you're going to have different integrals for each of these intervals. So on the interval from 0 to pi over 2, just to start analyzing what we'd have to do here, we notice that cosine is greater than this negative 2 over pi x plus 1 function. But on the interval from pi over 2 to pi, well, now the line is bigger than cosine. So my first integral, going from 0 to pi over 2, I'm going to have to be doing cosine minus parentheses that whole line in there with a dx. And for my second interval, from pi over 2 to pi, I'm going to have to do this line minus cosine dx. So just picking my answer choices carefully, because C and D look pretty similar. It looks like choice C has things being subtracted in the right order for each integral, so we will go with choice C. On this calculator-based problem, we have these regions in the graph here bounded by y equals x over 2 and y equals sine squared of x. We want just the sum of the areas of these shaded regions. So to do this, let me first start by labeling each of these functions. This x over 2 one I'm just going to call f of x, and this sine squared one I'll call g of x, just so I don't have to keep rewriting them every time. So now I essentially need an integral from left to right of top minus bottom. At least that's how I would do this if I wanted to guarantee getting positive areas without any special kind of symbols. The trouble is the top function in the first interval is different from the top function in the second interval. They flip-flop. So I either have to come up with two integrals, and then I'm going to have to figure out this intersection point right here, or I'm going to have to use one integral but use an absolute value around everything inside so that no matter what order I subtract things in, I'm still getting a positive value. I'm going to go the absolute value route, but I still need to find the intersection points at the beginning and the end of these shaded regions. So I'm going to set f of x equal to g of x, and I'm going to solve this on my calculator. Now, I don't actually need the calculator for this first intersection point. These are clearly intersecting at the origin, and if there were any doubt, if you plug in 0 for x, f of 0 is 0, and g of 0, the sine of 0 squared, is also 0. So clearly these are intersecting at 0, but what about this far point over here that's pretty close to 2? So let's go to the grapher for that one. I don't really mind going to my calculator to find this intersection point, because I know I'm going to have to use the calculator anyway when I turn around and take the integral. So I've got x over 2, and this is how you write sine squared of x on the calculator. This squared goes outside that last parentheses. And I'm going to graph these on the interval from, I don't know, -1 to 2. Based on the graph they gave me, I feel like that ought to capture everything I need to see. So -1 to 2 is my x min and my x max. Let's do zoom 0, zoom fit. And let's see what we can see. So there's my line. There's my sine squared function. And again, the only intersection I'm really concerned with is this one up here, because I don't really care about this middle one because I'm just going to use absolute value anyway. And this first one we saw was 0. So let me do second trace, option 5 for intersect. And let me move my little spider over to that last intersection over there and press enter, enter, enter to get 1.8491. So we had the intersection at 0 and also 1.8 and change. And I'm going to call that intersection point P, just so I don't have to keep rewriting that weird decimal over and over again. And on my calculator, because I need to actually plug this in, I'm going to quit out of my graph, and I'm going to store my last x value that I just got off of that graph as alpha p. So now I can pull that up on the calculator anytime I want. So my setup then for actually getting those areas, I'm going to have the integral from 0 to p of, and I'm going to do the absolute value now of f of x minus g of x dx. Now, it actually doesn't matter what order you subtract these in. Since you're doing absolute value around them, you could have done g of x minus f of x, and you'll end up with the same answer. So let me do the rest of this on the calculator. So I now need the integral, so math 9, from 0 to p, so alpha p. And in here I need absolute value, so let me do alpha window. That gives me my submenu from which I can get the abs function. And inside here I stored f as y1 and g as y2. So I'm going to do alpha trace y1 minus alpha trace y2. And I always put an x next to the d there. Press enter. And give it a little time to think. Usually has trouble with the absolute value. So we come up with 0.249 if we round that off to 3 decimals. And that gives us choice C. For this no calculator free response, we have L given as the tangent line to the graph of x to the n, where n is some constant. And this is happening at 1, 1. And this is only for n values greater than 1. First task is just to find the integral of x to the n, which is to say the area under that curve. So I'm just going to use my fundamental theorem, take the antiderivative, and then plug in 0 and 1. So antiderivative of x to the n, since n is a constant, I have to add 1. So I'm using the reverse power rule here. So we add 1, that's n plus 1. Dividing by that, we have 1 over n plus 1 times x to the n plus 1, evaluated from 0 to 1. And now to make my life a little bit easier, I'm just going to take this 1 over n plus 1 out of there, because this is all one big gnarly looking constant. And inside, I'm going to have 1 to the n plus 1 minus 0 to the n plus 1. You actually could, I guess, technically leave it like this, because n is considered a constant, and they said to find this integral in terms of n. But if you wanted to simplify this, well, 1 to the n plus 1 is just 1. 0 to the n plus 1 is just 0. So this whole brackets in here is just 1. Multiplying that by 1 over n plus 1, we just get 1 over n plus 1. For this problem, T is the triangular region bounded by L, the x-axis, and line x equals 1. We just want to show that the area of T is 1 over 2n. So this problem is kind of nice in the sense that they already told you what the answer is. You just need to prove that it's true. So in general, with triangle area, that's going to be 1/2 base times height. Now the height, we already know, it's a height of 1 for this triangle. So we just need to find a way to talk about this base, and probably we're going to have to express it in terms of n, because we have an area that has an n in it, and we know it's not coming from the height of 1. So I'm going to let B represent the base of this triangle. And in order to talk about B, I'm actually going to have to be a little bit tricky here, and I'm going to have to talk a little bit more about this tangent line, specifically the slope of this tangent line. So there's 2 ways to talk about the slope of this tangent line, and if we can set those 2 ways equal to each other, it's going to help us express B in terms of n. The first way of talking about the slope of this tangent line is by just taking the derivative of the function to which it is tangent, the derivative of x to the n at 1, 1. So derivative of this, using my power rule, is going to be just n times x to the n minus 1. And if I evaluate this derivative at the x value 1, well, I'm basically just plugging 1 in for x here, so I have n times 1 to the whatever, which is just going to be n. So this is one way of talking about the slope of this tangent line. Now, another way of talking about the slope of this tangent line, just using kind of rise over run reasoning, this tangent line, we are going up 1 and over, well, over the distance of this base for the triangle. So you could say that we have a slope of 1 over b, rise over run. And since the slope of this line also could be expressed as n, that means that 1 over b and n must be equal to each other. Whatever b and n are, these two quantities have to be the same because they both represent the slope of that tangent line. Well, if this is true, I can take the reciprocal of both sides of this equation, and I could write b equals 1 over n. And this is a way of talking about b in terms of n, just kind of using this equivalence on the slope of this tangent line. So a little bit tricky, you had to play around with things a bit, but that's how you could do it. So now, since a triangle area is just 1/2 base times height in general, we can write 1/2 times a base of 1 over n times a height of 1. And that just ends up being 1 over 2n, which is what they were asking us to prove. So we are done with this part of the problem. For the final boss battle of this free response, we're letting S be the region bounded by x to the n, L, and the x-axis, which they showed us here. They want us to find the area of S in terms of n. So it's going to be a function of n. And then they want to determine the value of n that maximizes the area of S. And just as a note here, I looked ahead at the rubric, and it turns out you don't need to justify that you actually found the max. You just needed to kind of find it. So we'll deal with that when we get there. But first, let's talk about this area of S. And to help me out here, I'm just bringing back some information from earlier on in this free response. So from part A, recall that the integral from 0 to 1 of x to the n dx was 1 over n plus 1. And from part B, recall that the area of t here, which might be helpful to know, we expressed that as 1 over 2n. In fact, we didn't find that ourselves. We just proved that that's what it was. They already told us that's what it was. So now I'm going to write the area of S as a of n. That's my function to represent that area. And that is going to equal, well, there's a few ways of doing this. So one way would be to figure out this intersection point on the x-axis and write an integral of x to the n from 0 to that spot, and then add to it an integral from that spot over to 1 with x to the n minus this line here. But that's kind of annoying, because then you have to figure out this intersection spot, and you also have to write the equation of this line. So another way to do it would just be to take the whole area under the x to the n curve and subtract the area you don't want, which is this t area. So that's how I'm going to approach this one. I'm going to write this as the integral from 0 to 1 of x to the n dx, and then I'm going to subtract the area of t. Now the reason I'm doing it this way is, well, if you look up here, I actually already know both of these things. This integral is just 1 over n plus 1. The area of t is just 1 over 2n. And now I actually have the area of S expressed in terms of n, which is exactly what they asked me to do. So I'm going to keep going with this because I now need to figure out the value of n that maximizes the area of S, but I've already done part of the problem, so we're already halfway there. So in order to get the maximizing n value, I'm actually going to have to take the derivative now with respect to n. Before I do that, I'm going to rewrite these in a format that's a little easier to differentiate. So this first one I'm going to write as n plus 1 to the negative 1. And this other one, I'm going to rewrite this so that I can use the power rule. So I'll write this as 1/2 times n to the negative 1. And now let me use the power rule on these. So derivative of this first one, this is going to be negative n plus 1 to the negative 2. And for this other one, I'm going to have plus 1/2 n to the negative 2. And I want to figure out, let's see, let me actually rewrite these in fraction form. But eventually I want to figure out where all of this equals 0 or is undefined. So let's see here. We've got 1 over n plus 1 quantity squared. And this other one is going to be 1 over 2 times n squared. And again, I want to figure out where all of this equals 0 or undefined. Now, the undefined piece of this isn't actually going to help me on this problem because we're undefined here at n equals 0, but they told us here that n has to be greater than 1, so we wouldn't even bother looking at that. We also could have this undefined if n is negative 1, but that's even more useless than 0 because, again, n has to be, at the very least, a positive number. So setting all this equal to 0 and just solving for values that make this whole thing come out to 0, if I multiply everything by n plus 1 squared and 2n squared, I end up with negative 2n squared here plus n plus 1 squared over here, so like so, and that's all going to equal 0. So I just multiplied by the common denominator of n plus 1 squared and 2n squared. And they basically just ended up flip-flopping who is in which numerator based on things canceling out. All right, so solving this, I can add 2n squared to the other side. And it looks like I can square root both sides. So that gives me just n plus 1 on the left. And on the right, this is going to be radical 2n, or n radical 2. Let me see here. I need to get n by itself, so let me subtract n radical 2 over to the left side and subtract 1 over to the right side. And to really get n by itself, probably be easier if I just factor out an n here. So that's going to be 1 minus radical 2 times n. And then just divide both sides by the stuff that's next to n. So at the end of the day, we have n equals negative 1 over 1 minus radical 2. So this is the only value of n that could possibly maximize anything, since this is the only critical value that's greater than 1. And I mean, if this doesn't work, nothing else would, because n just goes forever. They didn't give us an upper bound. They didn't give us a closed interval. And we said that we didn't have to justify the max anyway. So this is going to have to be good enough.